We've looked at the spring mass system now in a fair amount of detail. However, at this point I think it's helpful to look at the solutions in a more quantitative and exact way, especially when we talk about the kinds of solutions we get and what those might look like in terms of the actual motion of the spring mass system. To make this concrete, we're going to take a fairly simple example. We're going to use a mass of 1 and a spring constant of 25, and then we're going to vary the amount of damping, just like we did when we did the qualitative analysis. With the mass and spring constant given, this becomes our differential equation, and in this system we know that we can solve it by finding the roots of the characteristic equation, so we'll do that next. We get r squared plus cr plus 25 equals 0, and we'll go straight to the quadratic formula, minus c plus or minus the square root of c squared minus 4 times 25 all over 2, and that gives us negative c plus or minus the root of c squared minus 100 over 2. We saw earlier that critical damping occurs when we get repeated real roots, and those repeated real roots are going to happen when c squared minus 100 equals 0, or when c squared equals 100, or when c is equal to 10. We're not going to have negative c's for this, so just a positive 10. If c is less than 10, that's going to be the underdamped. There's not that much damping, and what that means is that our c squared minus 100 in the root is going to be the square root of some negative number, and that's going to give us an e to the at cos of bt type solution, or sine bt. So it's going to be oscillatory, and when we look at damping above that critical level, where c is greater than 10, then our c squared is going to be very large. We subtract 100, it's going to be positive overall, and that's going to be 2 exponentials as our solution, so no oscillations. So keep this in mind as we go through the demonstration, that when c equals 10, that's when we're going to get the repeated real roots, and remember that solution is this combination of exponentials of the same power, one just au naturel and one with a t out front. And it's going to be the transition between oscillatory and non-oscillatory solutions. As you go through the demo, keep this slide available and ask yourself these questions. As the damping increases over the whole range, what's happening to the graph and what's happening to the mathematical form? And also, near the critical damping specifically, so around c equals 10, what happens to the graph and what happens to the mathematical form of the solution? Here we have our demo field of view. Notice the differential equation up here at the top, and what we have on the sides are the solutions, y1 and y2, and there's a button we'll take advantage of later that'll show the amplitude when there are oscillatory solutions. This field here is the damping coefficient, like the value in front of the y prime, and this slider also controls the same thing in a slightly more intuitive way. This demo is available on the course website for those who have MATLAB. If you don't, that's totally fine. This is meant just to be a hands-off introduction, but if you do have access to MATLAB, it can be fun to experiment with. What we see right now is when we have zero damping, in other words, there's no friction at all, what we get are the pure oscillatory solutions that you see here. We also see the solutions are pure cos and pure sine, and the frequency that goes with them comes from this 25. It ends up being the square root of that value, and we get the angular frequency of 5 here. Now what do we expect when we first dial up the friction? Think about that for a second. Here's what happens if we let the mass go with a certain initial velocity, and it just oscillates forever, it bounces up and down. If we add a bit of friction, think what you expect the graph is going to do, and then we'll see what happens. Well, what we see is the same initial motion, going almost as high, but then because there's some consumption of energy, the oscillations become smaller in amplitude as time goes on. Perfectly reasonable from an energy perspective. How does that show up in the mathematics? Well, our R value would have a real part to it that would be negative. In this case, we'd have a negative 0.15 as the real, and we get an exponential decay as part of this solution. And the combination of the exponential decay and the oscillatory solutions is a decaying oscillation. And we can see what happens as we increase the friction level. As it goes up, the oscillations die off more quickly, which is exactly what you'd expect if there's more energy being consumed or dissipated through friction. Now, as we notice these gradual changes in friction, notice the gradual dropping of where the mass goes to in its first bump, and then the corresponding dying out of the oscillations more quickly later on. And honestly, after about 3 oscillations here, there are oscillations going on in this right-hand end. We can see that with the mathematical form, but the amplitude given by these exponentials is going to be so small after that time that we can't really see it, and for practical purposes, they would be negligible. And notice, we're nowhere near critical damping yet. Critical damping happens at C equals 10, and we're only halfway there in our slider. So even with this friction being far below the critical damping, it seems like the oscillations are damping out quite quickly and are fading quite quickly, even though the mathematical form again shows that they still would oscillate just with very, 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 very low amplitude. So let's creep up on 10. And in fact, well before we reach there, it just looks like one single bounce and then we're down, even though we still have cosines and sines. And then once we get close to the 9.9, so just on the threshold of being critically damped, it looks basically like a single bounce. It doesn't look like there's oscillations even though they're in the solution. And when we go past 10 and the solutions become purely real, for the characteristic equation we get pure exponential decays, we can't really tell the difference in all honesty. So keep that in mind when you're trying to visualize what critical damping means and what the solutions look like when things are critically damped. Now it is interesting to note, keep an eye on the shape of this curve and how quickly the oscillation, the one bounce of this oscillation, fades down now. As we increase the friction further, you can see that the time it takes to get close to 0 again is actually getting worse here because there's just so much friction in the system. The system bounces up and then just drags slowly back towards the origin. And when we get higher and higher frictions, it actually takes longer and longer to bounce back. So there is something about that critical damping being the fastest bounce back without overshooting that we can get. Higher friction leads to this slower decay afterwards. Returning back to 0 friction, so I'll jump back to 0. Here we have pure oscillations. What I'm going to do is also show the amplitude. Keep in mind, when we have the pure cosine sine, there's like a 1 out front. The amplitude, or in this case here, a 0.2, is actually the amplitude. I'm showing the negative 0.2 because things happen symmetrically during the simulation and during the motion of this spring mass system. Now if we dial up the friction a little bit, what we get is this exponential, and there'd be a coefficient out front, it'd be 0.2 in this case, and we'd see that this exponential is a barrier. The sine function goes up and down and up and down, up to touching that exponential curve. And what happens is we see the coefficient and the exponent get bigger and bigger, though negative, and what that translates to is faster and faster exponential decays, and we can see that in the shape of the curves. Notice there's also a little bit of other variation. The coefficient isn't always 0.2, it actually starts growing, and we start seeing that our solutions are still oscillatory, but they stay within this much more steeply decaying exponential curve, and we keep going. And by the time, again, we get to about 0.7, we see the one bounce, and then both exponentials, the mirror images here, are basically on top of each other for practical purposes, and we see this solution would flatten out if we're looking at it from the outside, even though it does have a cosine sine still in it. And then once we get to 9.9 here, we actually see the curves are super high, but then they drop super quickly because the exponential coefficient here is so big. And when we go to a value past 10, we can't actually talk about amplitudes anymore because there's no cosine sines, but the graph changes almost imperceptibly in that transition. Notice if we went to exactly 10 here, we would have the exponential of e to the minus 5 and t e to the minus 5. That's just that graph there. No real visible distinction between that 10.1 and 9.9, even though the solutions look dramatically different from the mathematical formulas. One last thing to explore after we reset the coefficient of friction to 0 is, just hypothetically, what would happen if we put a negative value in here? If we go back to our notes for a second, if we had a negative c value, well, this negative c, which is the real part, this negative c over 2, would become positive if c was negative. So if we had anti-friction, if you like to think of it that way, what would happen? Well, 0 is no friction at all. If we were to put negative 0.1 in here, what do we get? And try to imagine that before we see it. Well, the same thing we saw before, but in reverse. Before we had negative exponentials, so we had decaying amplitudes. Now we would have exponentially growing amplitudes. And the more non-realistic but bigger coefficient we put in here, the faster this curve's going to grow. Notice the amplitude's about the same as before, about 0.2 to start, but then it grows more quickly, and again, we would get just crazier and crazier things as we use a more extreme negative damping coefficient. So that's why we must get the signs right, or our predictions become quite suspect if we're talking about a physical system here. So hopefully that demonstration gives you a better sense of what happens as we start with a frictionless system, just a spring being let go and the mass oscillating afterwards, and what happens as we gradually increase the amount of friction in the system, and what happens specifically at the transition points mathematically when we hit the critical damping, what does the graph look like before the critical damping, and so on. We'll just pass through the critical damping one last time for demonstration. Notice we're creeping up on it there. And then we pass through the critical damping into overdamped and continue from there.